The question is, where does the problem, why is this causing a problem here? Why does our technique that is so good not start working as well here? The problem is discontinuity, and also cusps cause problems with this as well. If you look at the fittings that we're doing, what we're going to do is sample the graph at a bunch of points. And then what we do is we fit a quadratic on that interval. Well, that's a lousy fit. The quadratic and straight vertical lines don't mimic each other very well. And so we have quite a large error happening there when we try to fit a quadratic or use a quadratic to cover a jump. It's just not that great a fit. And you can even see when we use smaller and smaller intervals, you know, it's just not getting better and better. When we have a smooth function, like this part of the function, oh my God, it's gorgeous. Those dots, the lines between them and the lines of the function would be essentially identical. And so the areas would be essentially identical. So the problem area is all here, or as I mentioned, it can show up again with cusps. And it's the fact that we're using a continuous function to model something that's not. Or we're using a smooth function to model something that's not. Kind of like when we use polynomials to do interpolation. Well, if the function didn't do what polynomials do, things went wrong. This is going to be a problem for any fixed interval method. If I have this jump, and I can get higher accuracy, right? When we use more intervals, I get less error because the problem is only happening on a very, very short interval. But I don't get the performance boost I hope for because of the mismatch. And I'm wasting a huge amount of time. By using hundreds of points on this interval, I don't need that. I could use 4 points probably on this part and be fine as long as I use some really small points in the middle. So the problem we're facing with Simpson's rule is that we can't get around this poor accuracy problem / poor improvement as we refine the intervals when we use the same size interval everywhere. That is our real problem. By using the same interval size everywhere, that doesn't go well with cusps and discontinuities. Because the problem is in one place and we're trying to fit things over the whole entire length. We're spending a lot of work doing the integral over all the lengths that are really easy to do and not that much time on the points where the problem actually is. So it's kind of like a focusing of your attention. So one of the ways we can get around this is actually by doing or throwing away our delta x is always the same idea and using what's called adaptive quadrature. Here's the basic idea behind this. We're going to break our interval, and again, the MATLAB doesn't know what your function looks like. Here it's a nice pretty function that's periodic. If it was clever, it could actually cut right at the discontinuity. But we're trying to write a generic software here that works for any function. So the idea would be, let's take an interval like this and also cut it in half. And then let's fit, you know, a trapezoidal rule on this interval and a trapezoidal rule on the next interval. There we go. Actually, no, that's not quite right. Go up to the graph here. So we'll fit a trapezoid, and we'll fit a trapezoid there, and that'll be one approximation. Or we can fit a trapezoid and a trapezoid. And I think at a glance, you can tell that those two are wildly different from each other. I'm going to get very, very different areas from both of those. Well, that's OK, because what we'd say then is, all right, let's divide and conquer. And on this first interval, we'll cut them both in half again. And on this interval now, we've got the trapezoidal rule for this. Let's do that in green. And I'd have a comparable trapezoidal rule here and here. Well, that's starting to get closer. Those two are actually a little bit closer, and I'm drawing them poorly. Those two things are pretty similar, and more similar than just by reducing the interval size. Because I'm capturing a part of the function that's smoother, life is better. And you can imagine, well, I could do that again, and then maybe those two calculations would be very, very close. And I go, oh, OK, now I've done as well as I can do. I'm going to stop doing that interval, and I'll move on to the next one. But we subdivide as much as we need to until we get two calculations that agree, basically. And then we move on to the next interval. Do I need to subdivide it some more, or do I get my two answers being the same? And what you'll find is, because this problem area is fit poorly by any method we use, it's going to have to reduce the number of intervals, or use smaller and smaller intervals around there, whereas when things are smooth, it's going to be fine. It's going to use relatively fewer intervals, wider intervals. This is what happens if you actually run an adaptive quadrature on this particular function. There's points here, 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 here. It uses a cluster of them near the peak, and then here, 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 a cluster near here, a cluster near the bottom, and then spaced out. And what we're doing here is leveraging the power of both the interval size, so smaller intervals is more accurate by default, but also using advanced techniques like Simpson's rule, where if the function's smooth, I don't need that many data points to actually get a good fit or a good area calculation. So we'd see from here to here to here, that's not very many points that we need. Simpson's rule is going to do a fine job, though, because the function is nice and smooth. But then when we get to this jump, we're going to use a tiny, tiny interval. So even though Simpson's rule isn't the best thing for it, because it's a jump, it can't get that bad an estimate because it's such a small interval that I'm doing it on. So we get the best of both worlds with this kind of approach. To show you what that turns out to be, if we use 64 sample points, we get an error of 0.00001 with this adaptive quadrature using Simpson's rule in it. Compare that to the n equals 800 that we had, which was, with Simpson's rule, it gave us an error of 0.01, I think, which was 0.005. More work, less accurate. Less accurate. And that's because of the discontinuity needing a small interval to be accurate, but then we waste all the small intervals on the parts that don't need it.